Hi, this is a video to go along with section 3.2. I wanted to just do an example of a word problem, which we're starting in 3.2 and we'll keep working on. Once we get to 3.4, we're going to look at a bunch of word problems, so we'll come back to this. I'd like to just look at one where we solve by substitution. To start thinking about this, let's just see what we remember from geometry. Suppose a rectangle with length L and width W has a perimeter of 210 feet. Can you write a linear equation in two variables that models this situation? So we've got two variables here for sure, L and W. The length and the width of this rectangle. Do you remember how we calculate the perimeter of a rectangle? We want the distance all the way around, so we're going to count up the length plus the width plus the length again plus the width again. And we can shorten that as 2 lengths plus 2 widths. This is maybe a familiar formula for perimeter of a rectangle. 2 lengths plus 2 widths, and that should equal the perimeter, which is 210 feet. So all we're asked to do here is to write a linear equation in two variables that models this situation. I think we've done it. Let's try this. Suppose the length of a rectangle is 5 feet more than the width of a rectangle. Can we write another linear equation using those two variables that models this situation? Sure we can. We've got our variables length and width again. I know that the length is 5 feet more than the width. If I translate that, the length is 5 more than the width. I think that should do it. Let's say we want to find the length and the width of a rectangle. If the perimeter is 210 feet, just like in our previous calculation, and the length is 5 feet more than the width. So these are both conditions we talked about in the previous slide. And each of those conditions can be modeled using one linear equation in two variables. Well, if we want both of these to be true and we want to figure out what the length and width have to be for both of those conditions to be true, I think we can just solve the system of equations. Let's solve this, and this is a perfect setup for a substitution. I can take this value and plug it into the first equation for L. If I do that, I can solve this equation for W. That's 10 plus 4W equals 210, or 4W equals 200 if I subtract that 10 from both sides. Finally, division by 4 will give me 50. If my width is 50 and my length is 5 more, then my length has to be 55. So here we go, width of 50 and a length of 55. These are measured in feet. Okay, so this is kind of the idea. If we can write two linear equations using two variables to model our situation, maybe we can answer the question by determining the solution to that system. Let me remind you about our steps to problem solving. We talked about these in back in section 1.3. We'll familiarize, and in that step we want to define a variable in words, translate this time to a system of equations. Before we were just looking at a single equation when we translated. Solve that system, check that answer in the original problem, and then answer in a sentence with a unit of measure. A landscaper plans to dig a rectangular garden whose length is 5 feet more than the width. If the landscaper has 42 feet of fencing to enclose the garden, what should be the length and the width of the garden? Let's familiarize ourselves. I'm going to draw a rectangle to represent this garden. In this step, we want to define some variables for our unknowns, and it's asking me for length and width. Those are the unknowns. So why don't we define L to be the length of the garden in feet, and W the width of the garden, also in feet. Okay. So in my picture, I could have the length and the width here. In trying to translate this into an equation, well, I know the length is 5 feet more than the width. I think I can write that as an equation. That's similar to what we were just looking at. The length is 5 feet more than the width. The last sentence here tells me about the amount of fencing. Fencing goes all the way around that side of the garden, so that's going to be my perimeter. I've got that 42 feet of fencing to enclose the perimeter. Here is my system of equations. Our next step is to solve that system, and we'll do that using substitution. 42 is 2 times 5 plus W plus 2W. And we'll just distribute and solve this equation for W. And I get W to have a value of 8. If I stick that back in, my length I know is 5 plus my W value, or 13. Let's just check this. I'm going to put a tentative answer here in a sentence. The length should be 13 feet and the width should be 8 feet. And let's just check this, make sure we don't skip that step. 13 is 5 more than 8. So sure, that's true as I read through this. The length has to be 5 feet more than the width. That's true. And would this give me a perimeter of 42? Well, let's see. 2 times the length plus 2 times the width is 26 plus 16, which is 42. Yeah, that looks like it checks. The length should be 13 feet and the width should be 8 feet. An airplane has 152 seats. The number of coach class seats is 5 more than 6 times the number of first class seats. How many of each type of seat are there on the plane? Well, our first step is to familiarize ourselves with this situation and choose a variable for our unknowns. We've got 2 unknowns because we're writing equations with 2 variables. I think each type of seat is what we're trying to find, how many of each type of seat. So we've got coach class seats and first class seats. Why don't we pick some variables that represent those types of seats? Let's see, I'm not just going to say it's coach class seats. It's the number of coach class seats, right? Number of coach seats. And F, I don't want to say F equals first class. That doesn't make any sense. First class isn't a number, but it's the number of first class seats. So I want to make sure what I define here is something that represents a numerical quantity because that's what my variable is going to stand for. As I think about trying to translate some of this, well, my first sentence tells me the airplane has 152 seats. I know those are made up of the 2 types of seats. Let's see, I think it would be fair to say the number of coach seats plus the number of first class seats altogether is 152 seats. That looks like one good equation in 2 variables. What does our next sentence say here? Let's see, the number of coach class seats, that's C, is 5 more than 6 times the number of first class seats, and the number of first class seats is our value F. Let's see if I can translate that. The number of coach class seats is 5 more than 6 times the number of first class seats. I think that looks good. Let's solve this system. This is solved for C. So let's plug my second equation into my first equation. 5 plus 6F plus F equals 152, or 5 plus 7F is 152. And we can solve this easily enough for F. Looks like F, the number of first class seats, is 21. And if I stick that back in here, C, the number of coach seats, is 5 plus 6 times 21, or 5 plus 126. 131. Okay, let me write my answer over here. We'll come back and check it. I can say there are, how many of each type of seat are there on the plane? There are 21 first class and 131 coach class seats. We'll check that. I can check it in my system, but I'm going to check it in the words of the problem just in case there was an error with writing my system. The airplane has 152 seats. Well, I can check all together, 21 plus 131. Yeah, indeed, gives me 152 seats. That is checking in my first equation, but also in the words of the problem to make sure my equation was right. The number of coach class seats, let's see, there were 131 coach class seats. Is that 5 more than 6 times the number of first class seats? Well, I can check this. 5 plus 6 times 21. Yes, 5 plus 6 times 21 is indeed 131, so that looks good.